Hello, Math 135. This is Tracy. We are going to do an example of hypothesis testing for two populations. So the question we have before us, does smoking damage the lungs of children exposed to parental smoking? Forced vital capacity, or FVC, is the volume in milliliters of air that an individual can exhale in 6 seconds. FVC was obtained for a sample of children not exposed to parental smoking and a group of children exposed to parental smoking. So we have a table here showing our results. In our table, we have parental smoking, yes or no, and then the forced vital capacity in milliliters for the yes group and the no group, and S. Now that letter S tells us that we have a sample standard deviation. That's what S means. S equals sample standard deviation. So we have a sample standard deviation for the forced vital capacity for children exposed to parental smoking and not exposed to parental smoking. And we have N, the sample size for each of those two groups as well. So what we want to know is whether parental smoking decreases children's lung capacity as measured by the FVC test. In other words, is the mean FVC lower in the population of children exposed to parental smoking? That tells us we are going to conduct a hypothesis test. We want to know whether smoking decreases children's lung capacity by comparing two populations. Well, by comparing samples from two populations and seeing and testing, are those results different? Now, forced vital capacity is something that we measure in milliliters. It is not a proportion of children with a specific forced vital capacity. So we are comparing means, the mean forced vital capacity for each of these two groups. And S also tells us we're calculating a mean because we often calculate a standard deviation with mean results. We don't calculate a standard deviation for our proportion. We don't say the proportion of women who vote for Donald Trump is 60% with a standard deviation. No, we don't say that. So these are things that can help tell us that we are comparing the means for two independent populations. We have something that we are measuring in some units that is not a percent or a proportion of the entire group. So we want to conduct a hypothesis test comparing these two sample means to see if we can draw a conclusion as to whether the two populations have the same mean or not. So let's talk about how to do that. And I am also posting a solution sheet for Chapter 10, and that can help guide you through the process. You can use that for notes on the final exam as well. So let's get started. What are we testing? Two population means, two population proportions, or matched pairs testing. And like I said, this is two population means. So the test we use on our calculator, two samples, we have S, not sigma, not that funny little circle with the toupee. We have the letter S, sample standard deviations, so it's a two sample T test. Our random variable in words is a difference. Our random variable is x bar n minus x bar s, the difference between the mean forced vital capacity for children with non-smoker parents or not exposed to parental smoking and children exposed to parental smoking. Our random variable is those two population means, or are those two sample means being subtracted. So our null and alternative hypotheses, our null hypothesis for all testing in this chapter is that there is no difference between the two populations or between the matched pairs. Our null hypothesis, our assumption going in is always that the two populations or the two pairs of samples, the matched pairs, are the same. So we can write that in two different ways. We can have our null hypothesis say the two population means are the same, mu n equals mu s, or that the difference between them is equal to 0. Then the alternative hypothesis, as stated in this problem, is the mean forced vital capacity lower in the children exposed to parental smoking or not? Is the mean forced vital capacity lower in the children exposed to parental smoking? So our alternative hypothesis is that mu s minus mu n is less than 0, that the smokers' children have lower capacity than the non-smokers. So when you subtract that smaller number minus the bigger number, you'll get something less than 0. Or we could also phrase it, the alternative hypothesis is that mu s is less than mu n. Either way is fine, whatever makes you happy. So we want to figure out what the heck we put in our calculators and our TIs to figure this out. So you guys already know, you go to the stat button, you arrow over to tests, and then you scroll down or type in the number of the tests you want. And this is a sample t-test. So once you get into there, you'll see your screen and we need to know what to put into it. Now you'll see input, data, or stats. We highlight stats because our data is not being input through our lists. We are not going into stat, edit, L1, L2, L3, and entering data. We have been given summary statistics, so we highlight stats. And then we go down and we fill in what it tells us to. So our samples were given as smokers and non-smokers. So we need to call one of those number 1 and one of those number 2. And it really doesn't matter. Just make sure you pick it and you stick with it. So let's let the smokers be 1 because, hey, they came first in the list. Why not? And the non-smokers be 2 because they were the second column in the list that I pilfered out of another statistic. So under X bar 1, we take the sample mean from the smokers, which if you look at that chart is 75.5. We take the sample, that's what S means, standard deviation from the smokers, 9.3 from the chart. The sample size for the smokers, 30 from the chart. 2 is our non-smokers, so we take the sample mean from the smokers row in our table, 88.2 milliliters. We take the sample standard deviation for our smokers, 15.1 milliliters, and the sample size for our smokers, N equals 30. Now we have to match that next line to our null hypothesis. So, or I'm sorry, to our alternative hypothesis. So we looked at our alternative hypothesis, and our alternative hypothesis was that the mean for the children exposed to smoking, the smokers, is less than the mean for non-smokers. So our alternative hypothesis is that mu1 is less than mu2. Smokers have a lower, less than forced vital capacity than non-smokers. The next row is pooled, and we just always hit no. We are not pooling anything here. So pooled, hit no, and just always do that. Always, always. Now you saw there was an arrow, so we had to go down a little further. So you arrow down on your calculator, and when you highlight calculate, it doesn't actually show it. When I copied my screen, it was blinking on calculate, and I happened to capture it in an off blink. Anyway, you highlight calculate, and then you get the bottom information on your screen. And it tells you what you picked. mu1 is less than mu2. Ignore t equals. That's if you are, well, if you do things a different way, t is essential. We're not doing it that way. We're just reading our p-value right off the screen. And our p-value is sitting there under p equals. Ignore everything else unless you just want to verify your information, that you put in the correct sample mean for your first sample, the correct sample mean for your second sample, standard deviations. If you arrow down on your screen, you'll see the sample sizes, yada, 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 blah, blah, blah. But all we care about is that p-value. And that p-value is 1.3854, blah, blah, blah. Now, remember a p-value is a probability, so it cannot be negative and it cannot be greater than 1. So how on earth can we have a p-value of 1.385? Well, that's where that e negative 4 comes in. That e negative 4 means times 10 to the negative 4th. So take the decimal point in that 1.385 and move it 4 places to the left. And we get a p-value of 0.0001385, and that's far enough. If you go back into your two-sample t-test, and instead of highlighting calculate, you highlight draw, it will give you that graph on the top right of your t-distribution. And in the middle, you have 0. The difference between the two is 0. And if you went out to the left, you would go to 12.7, negative 12.7. That's the difference between the two. And you would find a little tiny bit of blue shaded in. Well, we can't even see it. It's so far out there. And what this p-value tells us, a p-value always tells us the probability of getting our results, our sample results, or more extreme if the null hypothesis is true. The p-value is the probability of getting our sample results or more extreme if the null hypothesis is actually true. In the words of the problem, the probability of getting two samples such that the mean forced vital capacity for children exposed to parental smoking is 12.7 millimeters less, or even more less than that, then the mean for children not exposed to parental smoking is only 0.0001385. That's tiny. The probability of getting that big of a difference, 12.7 milliliters or more, where the mean for children exposed to parental smoking is 12.7 millimeters or more less than the mean for children not exposed to parental smoking, is tiny. That probability of getting those results is so tiny if the null hypothesis is true that we can't even see it on a graph. We don't even care about a significance level at this point. That p-value is so tiny that for any reasonable significance level, alpha equals 5%, 0.05. Alpha equals 2.5%, 0.025. Alpha equals 1%, 0.01. Some really crazy testing, they will choose alphas even smaller, 0.5% or 0.1%. But any of those, our p-value is so much smaller than alpha that the probability of getting our results if the null hypothesis is so true that of course we doubt the null hypothesis. These are crazy results if the null hypothesis is true. So we reject the null hypothesis. And then we need to put that into words that a layperson could understand. Our data support the claim that parental smoking does damage the lungs of children exposed to parental smoking. At a 1% significance level, we have evidence to support the claim that lung capacity, as measured by the forced vital capacity test, is lower in children exposed to parental smoking. And when you're giving your results, it's a good idea to include your significance level and your p-value. That way somebody can look at your results and say, well, maybe what if I don't agree with your alpha? What if I don't agree with your significance level? Does that change the ultimate claim? And showing the p-value shows that, nope, Our claim, we really believe it because that p-value is just so tiny. Okay, so this was section 10.1, comparing two population means with independent samples. Our next examples will be from the other sections.